For number 1 on the homework, we're asked to draw the Lewis structure of each molecule, indicate whether the molecule is polar or nonpolar, list all the type of intermolecular forces, and then circle the most significant of each of those. So on the left are our 3 intermolecular forces. And then I told you guys about a 4th one called ion-ion, and that's anytime you have a metal and a nonmetal. So the next one we have is carbon dioxide. It has a total of 4 plus 2 times 6. That gives us 16 valence electrons. And then over on the right here, I'm going to draw carbon dioxide. Carbon goes in the middle because it makes more bonds than oxygen. Carbon makes 4. And then when I fill in all my electrons, it turns out in order to get a full octet on each of these, we're going to have to do a double bond between carbon and each oxygen. So there's all 16 electrons. And to say whether this is polar or nonpolar, even though oxygen-carbon bond is polar, because they're pulling in opposite directions, this is actually a nonpolar molecule, just like a tug-of-war. That was in our Kahoot. And so this guy is nonpolar. That means the only intermolecular forces are London dispersion forces. So any nonpolar molecule has only London dispersion forces. For pH 3, I'm going to count my electrons, and you end up getting 8 valence electrons. Hydrogen always goes on the outside, so I'm going to get phosphorus, single bond to each hydrogen, and a lone pair of electrons on top of the phosphorus. You might remember this as AX3E, makes trigonal pyramid. You don't necessarily need to know that right now, but it's definitely going to be a polar molecule because of the lone pair on the central atom. And everything has LDF. Because this is polar, it also has dipole-dipole. So that's going to be the most significant or the strongest of the intermolecular forces. The next one is propane, C3H8. I'm going to count the electrons, although typically for these bigger molecules we don't. And the reason why is carbon always makes 4 bonds, hydrogen always makes 1. So that means all the carbons have to go in the middle. 3 carbons makes 12 electrons, plus 8 hydrogens makes 8, so 20 electrons. But with carbon-hydrogen stuff, we usually just draw all the carbons in the middle and then make sure each carbon has 4 bonds. And if you add the 2 electrons from each bond, you end up getting 20 total valence electrons. So because the carbon-hydrogen bond is a 0.4 difference in electronegativity, and also because this is symmetrical, you have hydrogen spread evenly throughout. This is a non-polar molecule, and you might want to memorize that. Anything that's just carbons and hydrogens is going to be non-polar. And so this is LDF only. For the last one, C4H9OH, I'm going to draw this one a little more quickly. If you Google this to look at the structure, that's fine. What you get is the 4 carbons in a row. Oxygen makes 2 bonds. And then you get single bonds to each of the carbons. This one takes a little bit longer to draw, so I'm going to kind of speed through it. If you counted electrons, there's a lot here. But after all the bonds, there's 4 extra electrons. And those go on each side of the oxygen, 2 lone pairs. So this is called butanol in real life. And it can hydrogen bond. So this guy's polar. Anything with an OH on it is polar. And anything with an OH can hydrogen bond, so it has to be polar. LDF, because it's a little bit polar with that OH, dipole-dipole. But you can remember that anything with hydrogen bonding is automatically dipole-dipole, and of course everything has LDF. So now we have to decide, well, what order do these go in? Well, anything with hydrogen bonding is going to be pretty high boiling point, but we said way above the other intermolecular forces is the ionic, so CaCl2 is the most. There are two molecules on here that can hydrogen bond, and because C4H9OH is a bigger molecule, it has hydrogen bonding, and it's also bigger molecules have more London dispersion forces. So C4H9OH is going to be second. They can both hydrogen bond. However, more London dispersion forces for bigger molecules makes that one bigger. NH3 is going to be next because it can hydrogen bond. And then we have to look at the dipole-dipole molecules. We have pH3, we have CO2, and sorry, CO2 is LDF only. PF3 and pH3 are the two. So PF3 is bigger. So the bigger the molecule, so they're both polar, but PF3, because F is a bigger atom than hydrogen, means it's going to have more London dispersion. That's bigger than pH3. And then my last ones here. We have C3H8, CO2, and H2. So those ones are all London dispersion forces. And again, London dispersion forces depends on the size of the molecule. The bigger the molecule, the more the electrons can sway back and forth. Slightly bigger than CO2. Then hydrogen is the smallest. So if you look up the boiling points for all of these, you might get a different order because there are a lot of other factors involved. But if we're just looking at intermolecular forces, CaCl2 has ion-ion. That's the strongest intermolecular force. It's so strong we just call it an ionic bond. The next highest category is hydrogen bonding. And then dipole-dipole. And then London dispersion is generally the weakest. For all of these, though, the bigger molecule usually wins because they all have London dispersion forces. So if we take out ion-ion, because that one's so strong, the reason why C4H9OH is stronger than NH3 is just because it's a bigger molecule. They both have hydrogen bonding, but C4H9OH also has bigger London dispersion forces. It's just got more electrons. PF3 is bigger than PH3, so even though they both have dipole-dipole, well, that should say LDF. And then C3H8, CO2, and H2, those are in order of size. So within one group of intermolecular forces, the size has an effect.